Hello everyone, welcome to the Introduction to Derivatives. In this section, we will learn how to find an instantaneous rate of change. Prior to this point, you've only learned how to find an average between 2 points. Today, we will learn the derivative definition through an example. Now, what I just said here is that we've only learned how to find the rate of change between 2 points, and what I mean by that is we've only looked at the rate of change of a linear function. In other words, we've gone over a certain amount and gone up a certain amount, and we've looked at the rise over the run to determine what the rate of change of that particular linear function is. What we've never done is looked at something like a parabola and figured out the rate of change of that parabola. And we're going to learn how to find the rate of change of something that's not constant today. So let's go ahead and get started with an example. We have a ball rolls down a ramp so that its distance s from the top of the ramp after t seconds is equal to t to the power 2. So the distance is represented by this function s of t equals t squared. Let's graph the function with these certain time values. The first one, we have a 0, and so we plug in 0 into the t spot, and we have a 0. When x is 0, y is 0. Or I should say when t is 0, the distance is 0. And we plug in a 1, 1 to the power of 2 is 1. We plug in a 2, 2 to the power of 2 is 4. We plug in a 3, 3 to the power of 2 is 9, and then we plug in a 4. 4 to the power of 2 is 16. And we can see here that this is a rate of change that's not constant. At 1, we're going a different rate than we are when we're at 4 seconds. We can see that the ball is increasing in speed as the seconds go on. And think about that. If you put a ball on the top of a hill and it rolls down the hill, it will pick up speed and go faster and faster and faster as it rolls down the hill. So this is not constant. So I'd like to figure out what is the instantaneous velocity right at 3. What is the rate of change right at 3 seconds? Now velocity is equal to feet per second, which is the rate of change, which is literally the slope of the function. So we're going to look at the change in feet over the change in time. Now that triangle there in front of the s and the t simply means change. And to find the rate of change, we're going to go back to the good old formula that we have always used, the difference in the vertical values over the difference in the horizontal values. And if we were to do that with just a single point at 3, we would come up with a problem, because we would subtract the 3's down below, and we would end up with division by 0, which is impossible. So we have this problem when we try and find the instantaneous rate of change at a single point, and that's the division by 0 problem. How do we get around that? And that's why this derivative definition exists, because we're trying to figure out the instantaneous rate of change at a single point. So up until now, when we have found the slope, we have used 2 separate points on a line. We figured out the average between the 2 points. Now we're looking for a single point. We come to a problem. Division by 0 is impossible. Let's see how close we can come to finding the instantaneous velocity by finding the average between 2 points. So we're going to use these time intervals from 3 to 4 seconds, from 3 to 3.5 seconds, from 3 to 3.1 seconds, from 3 to 3.05 seconds, and just see what happens as we get closer and closer and closer to that single point. So let's first look at the average rate of change between 3 and 4 seconds. So we go over here, and this represents 3 and 4 seconds here. And so I want to figure out what's the rate of change between these 2 points here. And literally it's this line that goes through these 2 points. And this line here as we see from the previous slide, this line has a rate of change of 7. We have a rate of change of 7. But we could get a better idea of what the rate of change is at 3. So we get even closer. And then we jump to 3 and 3.5. Let's try and get closer to 3 to see what the rate of change is right at 3. And so instead of 3 and 4, we're going to go to 3 and 3.5, and we want to figure out the rate of change in between those 2 points. And so we draw a line between those 2 points, and this line here represents the rate of change in between 3 and 3.5, and we're like, no, we could get even closer. Let's go ahead and try something else. Let's try 3 and 3.1. So we get even closer, really close to 3, and we draw our line here, and we could get even closer, and we see that our rate of change is getting closer and closer and closer and closer to 6. It looks like we're approaching 6. And, we see that our average is getting closer to 6 there, but we don't want to get the average. We want to see what it is at a single point. So we're going to use what we're working with right now and try and come up with a definition that describes how to find the instantaneous rate of change. That's what we're working towards right now. But let's talk about these lines here. These are known as secant lines. Secant lines are the average between 2 points. And what we want to find is the slope of a tangent line, which is actually the rate of change that only touches the graph at 1 point. So we want to see what happens as we get closer and closer and closer to 3. So let's try and generalize the pattern that we've been looking at here. What I've done here is I've rewritten the slopes, the rate of change, so that the 4 is not just a 4. The 4 is represented as 3 plus 1. I'm showing how far away from 3 we actually are. We're plus 1 away from 3. And then 3.5, we're actually plus 0.5 away from 3. And then here at 0.1, we're actually 3.1, we're 0.1 away from 3. And then right here, we're at 0.05 away from 3. So I rewrote the slopes as a little bit differently. We're looking for the rate of change right at 3, and so I wrote the slopes with how far away we are from 3. So let's go ahead and try and generalize what's going on here. Let's call 3 that rate of change that we're looking for. Let's call that our time value. Okay, and let's call the distance we are away from 3 an h value. Okay, so each time we're going to place a t in the 3 spot, and the distance we are away from 3, we're going to call that the h value. So I would say here that if I was going to generalize this overall pattern, I would say that this is a t plus h squared minus t squared over t plus h minus t. So this is a generalization of our pattern so far. Okay, let's generalize even further. We know that the function is s of t equals t squared. So I could say that in minus t squared, I could say a minus s of t instead. And in this spot here, we could say that spot corresponds to s of t plus h. And down below here we have the t minus t, so we could just write an h down below. So this is a generalization of our pattern, and what we were looking for is the rate of change right at 3. And so we were looking at what happens as we get closer and closer and closer to 3. So essentially we were looking at what happens as that h value gets closer and closer to 0. Remember that h value is the distance we are away from 3. So we're looking literally at a limit as h goes to 0. So a lot of times books will use f and x instead. And so this is our definition here. We have to let y equals f of x denote a function f, and the derivative of f at x is denoted by f prime of x. So that little apostrophe there is known as the prime, the derivative. And that's equal to the limit as h goes to 0 of f of x plus h minus f of x, all divided by h. So let's get some experience using this particular derivative. I'd like to figure out the exact derivative right at 3 using the function that we were dealing with. S of t equals t to the power of 2. So, well, actually, our derivative right here, I copied and pasted the definition with f and x, but we can pretend for a second that we're looking for the derivative when s is in the place of f and the t value is in the place of the 3 there. So let's get the setup first, okay? We have s prime of 3 is equal to the limit as h goes to 0 of s of 3 plus h minus s of 3, all divided by h. So let's plug in. What we want to do from here is we want to plug in 3 plus h into our t spot, and we want to plug in 3 into our t spot as well. Let's see what that looks like. Okay, so I've plugged in, and from here it's a matter of the algebra skills to figure out this limit. And first thing I want to deal with is the 3 plus h squared. That means 3 plus h times 3 plus h, which means 9 plus 6h plus h squared. So we have 9 plus 6h plus h squared minus 9 all over h. And we're looking for what this is equal to as the limit of h goes to 0. Let's go ahead and simplify some things here. The 9s will cross each other off. 9 minus 9 crosses off. And I'm going to pause and erase some things, and we'll simplify from there. Okay, so we have the limit as h goes to 0 of 6h plus h squared over h. And we can simplify that. We could actually factor out an h from the numerator, and that gives us h times h 6 plus h, and we can cross off an h in the numerator and denominator, and we are left with the limit as h goes to 0 of 6 plus h. And there's nothing that we can do from here, and so we plug in h equals 0, and we have 6 plus 0, and that gives us a 0. And so that means that s prime of 3 is equal to 6. In other words, the rate of change right at 3 is equal to 6. If we go back to that picture right here, that would mean that the slope of the tangent line right at this particular point is equal to 3. In other words, for every one that we go over, we go up 6. And that is the rate of change of our particular function for this one here at 3. I will continue on in another link in a sec.